Thank you very much for the nice introduction, and also for inviting me and giving me the opportunity to give this presentation. It's about cooperative verification. So the idea is, we have lots of verification tools already, as witnessed by the competition, and we need to leverage all possibilities that we have. And this can be done by combinations, and this is why I want to emphasize this point a bit, and this is why what I want to achieve with my presentation. Okay, so the context of the work is software verification. Some of the principles apply also to systems verification, but if I talk about concrete examples, I talk about software verification and automatic software verification. So I'm not talking about deductive tools for software verification, but automatic ones. So what is it? The input is a program, for example, a C program or Java program or so. This has a specification also, and this is given to a verification tool, and the verification tool spits out, yes, true, the program satisfies the specification, and here is the witness as a justification for this, or here is a bug report, the program does not satisfy the specification, and here is a witness that explains how to reproduce the bug. So that's a setup basically. And what is the status on verifiers? So 20 years ago we had a lack of verifiers. We had actually only 3: BLAST, SLAM, and setups. But now currently we have an abundance of verification tools. So I just counted them over the last 10 years, 76 tools for Java and C verification were developed. 76, right? And so I want to talk a little bit about this first. Also, the maturity of the area. So Kirill has mentioned one competition, the SVComp, Competition on Software Verification. This is an off-site competition about automatic tools in a controlled environment. There's another competition, RARES, which is also off-site, but it's freestyle, so everything is allowed. Resources are not restricted in any way. There's a test competition where tools are generating test suites to achieve certain coverage. And there is Verify This, which is a competition where tools and verification teams are evaluated. So there, it's all about the interaction between a team and the verification tool. So there's lots going on there, and now let me focus on the one competition, software verification competition. So that started for the first time 2012, and at that point we had only a bunch of tools, as is shown here. 10 tools, and every year it became more. Every year, more tools participated. Many tools participated several times. There are tools that participated in each of the competition, and it became more and more and more, right? And now we have so many tools, and I think this year more than 40 tools participate just in one edition. Now, why is there not the verification tool that can do everything and that wins every time, right? Because the verification tools have different strengths. This picture shows the various categories of the competition. For example, there's a category on reachability, there's a category on memory, safety, on concurrency, and so on. And as you can see, in each category, there's a different tool winning, right? So it's not really that one tool is the best of all of them. So this is one thing, different strengths. There's another thing. This is too small to read, but I want to emphasize that there are many different techniques that are implemented in these tools. So on the x-axis, there's a list of techniques like CEGAR, predicate abstraction, k-induction, numeric interval analysis, shape analysis, and so on and so on. And on the y-axis, you see all the tools. And a check mark means this tool implements this technique for participating in the competition. As you can see, there are techniques like bit precise analysis that almost every tool implements. because in programs, in C programs, we don't have integers in the mathematical sense, but the type integer is used for bit vectors, right? And yeah, there is also concurrency support, which is often supported, but there are also techniques that are not so much used in the tools, right? But the big picture is there are many tools, there are different techniques, and different tools implement different techniques, right? And this maybe explains what we saw earlier, that there is no one tool that that wins all categories. I want to give you an example of a tool. So CPACHECKER is a framework for software verification, and it implements a lot of these techniques. It implements CEGAR, interpolation, configurable program analysis, adjustable block encoding, conditional model checking, verification witnesses, and so on, and many different abstract domains like predicates, intervals, BDDs, right? And there are several different analysis approaches that are also implemented there: predicate abstraction, impact algorithm, bounded model checking, K-induction, IC3, explicit state model checking, and so on. Recently, we added interpolation-based model checking. So you see, there are also frameworks that implement the most well-known algorithms, and yet this tool is not able to, to win the competition in every category. And why is this? Because really every category requires different strengths to play out. And it's about how to combine different techniques to get the maximal power out of it, right? So we have verifiers with different strengths. There are plenty of such tools. Now, what can we do? And my proposal is try to investigate cooperative approaches for verification. So what I want, my vision is, so currently, we have libraries for data structures. Then on top of this, we have libraries, for example, SMT solvers. We can use them as libraries. And on top of all these libraries, we build software verification tools. Now, what I envision is, let's put a layer on top of this and use verification engines like a library, right? So that if somebody constructs a verification tool, this developer can leverage and can use all the verification technology that is available in other verification tools. Currently, this is not possible. Why? Because there are no interfaces defined. There are no clear interface. What are the objects that I have to pass through? If I make a library call, what is the input? What is the output? And this is what I think is an open problem, and we need to solve this somehow. And there are some objects already that we have identified: conditions, witnesses, test suites that can be passed around and exchanged. But this is not enough. We need more of this. And this is what I want to emphasize on. So there are success stories, SAT and SMT, right? They have a clearly defined interface, a clearly defined problem. And this is just successful because you can use all these nice tools as libraries. So what kind of combinations do we have? If you look at this picture here, we have combination approaches. These can be basic or combination. And the combinations we can partition basically into two kinds. One kind is, I call it off-the-shelf components, which means I use in a black box manner components that I do not touch. I use them as they are. And on the other hand, I have source code components where, for example, reduced product, or conceptual integrations, like I go into the source code and integrate together several approaches. But here I have to program. On the right-hand side, in the source code components, I have to program. I have to invest development effort. And on the left-hand side, we have combinations that we can achieve without programming inside the verification tools. And as example, portfolio is a very old technique. It comes from from economics, right? A portfolio means you want to distribute the risk, so you want to invest. Here it means invest time and computational resources to several solutions. And there's a parallel portfolio where you basically start several verification tools with the same problem, and you take, whoever gives the first result and then kill the others. And there's also sequential portfolio where you start one tool with a limited for a limited time, but with the full resources, and then the next one, and then the next one, and so on. Then there's also algorithm selection, also very old technique, also more than 30 years old, this technique. So you take the input, you analyze shortly this input to find out, which algorithm works best on this input. And then you select this one particular approach and start this one. So this one gets the full resources and the full time that you have, right? So this is different from portfolio. And then cooperative. This is the rest, basically, and this is what we, I think, need more, where you have two tools, and those tools communicate with each other. So they give intermediate results to the other, and they help each other to achieve the goal. And this is what we don't yet have so much, right? Portfolios, algorithm selection, this is out there. There are even ways to half automatically construct those tools, but for the cooperative, it's not so much. There's not so much available. So to approach the problem, we said, okay, we need to think about what kind of tools do we have, how do they behave, and what are they actually in terms of, pragmatically. So we have, for example, an analyzer like this, second in the first row here. A verifier is an analyzer that takes as input a specification and the program and spits out a result and a witness. Right? If you have, for example, a reducer is a transformer who takes as input a program and a formula that describes what should be reduced, and the output is a new program that is reduced in a certain manner, right? And so, for example, then we can combine tools. For example, here a conditional verifier can be constructed from a reducer and the verifier. I will explain this later how it works. So we have a program and a condition. This is given to the transformer. This gives a new program, and the program is given to the analyzer, for which you can instantiate with a verifier. And this takes the specification of the program and produces a result and the witness, right? Or here, for example, you can say an analyzer takes a program and a specification, spits out a result and a witness. The witness, so if it is a violation witness, one that gives us an error pass through the program that violates the specification, we can transform it to a test case, give this test case to some presentation tool like a debugger or so that plays the test and shows us the result, right? So this helps a bit to understand what kind of types of programs we have. And then let's try to think what cooperative verification means. So I think cooperative verification is if we have identifiable actors that pass information in the form of identifiable artifacts towards the common objective to solving the verification problem, where at least two of these are analyzers, right? So let's put examples for this notation, like what is an identifiable actor? That could be an off-the-shelf component. For example, a verification tool that is published somewhere, in an archive of an artifact, for example, right? And we can take the binary from it, start it, or it could be a web service that provides the verification behavior. What are artifacts? Well, the artifacts are the things that we pass around, objects to give to other tools. So there are programs, obviously. There are specifications, there are witnesses, there are abstract readability graphs, there are proofs, there are test suites, and so on, right? And what is the verification problem? Mainly and obviously, the verification task is, there's a program, there's a specification, find out whether the program satisfies the specification. But maybe we should have more fine-grained verification tasks. For example, say that, okay, Here's a test task, develop a test that exploits a certain situation. Or here is a pass through the program, check whether this pass is satisfiable, that this pass is feasible, executable in reality, right? Or here is an abstraction for the program, how can I refine it? So these are also verification problems, and maybe these need to be addressed. So now for the rest of the presentation, I want to give you some examples of how to go ahead a little bit with these, with this cooperation approach. And the first example or application, I call it A1 to whatever, and application 1, I want to explain software verification with witnesses. So what is this? Because witnesses are really so important in our verification ecosystem. So given a program and a specification, the verifier spits out the result. It is true that the program satisfies the specification or false, right? But it is wrapping everything together in a witness. And this witness explains why the tool says true or false. It gives justification for it. Just as an example, so if the outcome is true, then this means there needs to be a proof, right? And this proof obviously had to use some invariance for loops or so. So this witness must contain the invariance for the loops. Or if it is, if the result is false, then this means we have a counterexample against the specification. So this witness must contain, a path through the program that violates the specification, right? So this is what a witness is. And now we need a second component, what to do with the witness, right? We can validate that the result of the verification tool is correct. How can we do this? We have a second tool, which is almost like a verifier, but let's call it Validator. And the Validator takes as input a program, a specification, really the same program, the same specification, and the witness that the verifier produced. And the Validator is trying to establish the proof that the verifier has found. It can be a different proof, but it uses the information from the witness to construct this proof. And this makes it maybe easier, right? So from SAT, right? Finding whether a formula is satisfiable is NP complete. But if you have the satisfying assignment, checking that this formula is really satisfiable with this given assignment, this is P, right? So, and here, of course, software verification is undecidable and so on, but you have an intuition that checking, if you have a solution already, checking that this solution is correct is easier somehow. So the validator constructs its own proof with the help of the witness. And it also says then in the end, true or false. This enables a lot of options for us. For example, we can now say, in the last 20 years, I would say, we were concerned about making the verification tools more correct, right? Verification tools are software. Software is developed by humans. They contain bugs, right? And obviously, you sometimes get a proof that is somehow wrong for, there's a bug in the program or so. So, and in the past, we were concerned of making these verification tools more and more better, reduce wrong answers and so on. And it's pretty good. There are tools in the competition that don't produce any wrong results. And the benchmark set is about 15,000 verification tasks. So this is pretty good, but still, maybe we want to have verifiers that are not giving precise answers, but maybe, imagine we can use machine learning to come up with invariants, and then we are not sure whether these predicates are really invariants, right? But if we have a technique that tells us that the result is validatable later on, right? Then we can accept this. Okay, give me your witness. Maybe it contains meaningful invariance. I will find out with the validator, right? Or a verifier says, okay, I have found a bug. the validator says, okay, give me, right? And I will check whether this is really an error pass. And maybe this way we get more efficient strategies for verification if we do not have the requirement to be precise. So far about witnesses. Next, we have worked on a small domain-specific language to make it easier to combine verification tools. So, for example, here in this little algorithm, I just wanted to express that so we have input, program, and specification, and we want to verify it and validate it together, right? And what it does is, in the first line, we instantiate a verifier from an archive for the verifier ultimate automizer is the name for a verification tool, and store this in a variable. And then we create a validator. Let's say take CPACHECKER. So we have a variable. So this variable is of type validator, and then we can compute a result, verifier.verify, right? And then we have the result. And if the verdict of the result is true or false, then we validate it. So we start the validator to validate it. Same program, same specification with this witness, right? And then we return the result and the witness in the end. And so, because usually this is done by writing bash scripts or Python scripts, right, to call various tools and so on. And this CoVeriTeam is the name of the language and the tool. It not only gives the output of one tool as input to the other tool, but it also installs the tool. It executes these operations in a safe environment. So it starts a container, executes it in a container, so that you can basically use this on your laptop without having the major security concerns anymore. Okay, then just to give you an impression, even without cooperation, you can achieve a lot. So let's look at simple combination. So we have experiment with portfolio construction. We have published this at ETAPS this year, and what we did is we put together a parallel portfolio of several verifiers that we took from the last competition, and we had looked as industrial programs. So the benchmark collection has some programs from Amazon Web Services, and Amazon uses CVMC in their continuous integration. So we are finding that according to the competition, 70 were solved and 8 answers were wrong. And if we take this CoVeriTeam parallel portfolio, where we have not touched those verifiers. We took them as they were published on Zenodo or so, and just wrote a little, CoVeriTeam program to combine them. And we could solve more than 140, which is double, and with less wrong results. Right. So even with naive combinations like parallel portfolios, we can achieve a lot. But we can even do better. Suppose there is a verification task consisting of a program and a specification. And suppose a verifier A can verify a little bit, but not everything, and the verifier B can verify a little bit, but another part, but also not everything. So how would it be if we could combine these verifiers to prove, all program paths? And we have experimented a bit, and we found many example programs where this actually could help. So the idea is conditional mode checking. So what we do is the first verifier, we turn it into a conditional verifier. What is a conditional verifier? Conditional verifier is a verifier that spits out the answer true under condition psi. And the condition psi describes the state space that was successfully verified. And everything that's outside of this condition, the verifier doesn't tell anything about, right? And then this condition can be given as the input to the next verifier, right? So this is the condition of what is basically, this describes what was verified as correct by the first verifier. This is given as the input together with the original program to the next verifier. And this verifier is told, please verify that this program is correct, but you can ignore everything that's described by this condition. Right, and now this verifier can play out the strengths on the remaining state space. And this works out pretty well, but we were hoping, this was published 20 years ago, and it didn't really, it was not the technique that everybody implemented, and we were thinking why, right? And the idea is maybe it is difficult to implement, the logic to read in a condition, parse it, and construct a cross product with the program and so on. So maybe this was too difficult. So what can we do to make this approach accessible more? And so given a verification tool, remember, we have more than 50 verification tools, right? So how can we use these 50 verification tools? Is it possible to turn a verifier into a conditional verifier without implementing the logic to parse and understand the condition? And yes, it is possible. And once I tell you, you will find it trivial. So this is the conditional verifier, and it is using an ordinary verifier as a backend. And what we do is we take the input program and the condition and use a reducer to reduce the program to those passes that are not described by the condition. Right? So this is what we call a residual program. It's the program, but everything that was proved correct is removed from it. Right? And then we give this to an ordinary verification tool that verifies it and takes this as an ordinary input program. Right? So why is this good? The exchange format is something that we all know. It builds on this, it's a C program. This is defined already. So we have not introduced a new language, a new object that people have to adjust and implement something for, which was the obstacle before, right? Okay, so next example. CEGAR is a verification approach where in an iterative manner, an abstraction of the program is constructed. So the program is given as input to a so-called abstract model exploration. And this component explores the program and tries to find either a correctness proof or error path that violates the specification, right? If it finds the correctness proof, then we are done. We can spit out the correctness proof and finish. But if it has found a path to the program on which the specification is violated, then this violation might be due to the over-approximation, right? Because it's an abstract model exploration. So we have to give this potential counterexample to what we call a feasibility check. And the feasibility check takes the counterexample and verifies whether this is, according to the C semantics, really executable. And if it is so, if it is executable, then this means this is really a bug, and we can report that the program is incorrect. But if it was due to the over-approximation, then what can we do? We have this infeasible counterexample, and we give this infeasible counterexample to another component, which we call precision refinement. And this precision refinement now inspects the infeasible counterexample to learn from it some facts that we can use to as a precision increment in the model exploration to not visit this counterexample again, right? So we learn how to improve the abstraction of the program, to refine the abstraction of the program such that we are closer to the actual C semantics, right? And this goes on until either resources are we are out of resources or timeout or so, or we have either this or this answer, which surprisingly often happens. So now we have these three components, and what we see in practice is that many verification tools have implemented this technique. This is really well known and state of the art, but every developer of a verification tool implements it from scratch. So how about using an overall algorithm like this and use off-the-shelf components for these three? This is what we tried. So CEGAR defines already what are the input-output interfaces here, but we don't have exchangeable instances so far. So what we tried to do is generalize CEGAR and to break it into pieces, decompose it into the three components, and then allow exchange of components. Because if we allow exchange of components, then we can replace one component by a better one. So what we did is we tried to make use of these witnesses, because in the verification community, all the verification tools, they support witnesses, they spit out witnesses. So what we do now is if the abstract model explorer finds a counterexample, we dump this counterexample in the format of a violation witness, right? And then we ask a feasibility checker, which is like a witness validator, right? Because if this is an infeasible counterexample, then the validator would find out that this is not a realizable path. So we can use existing components here. There are 10 validators around. We can use all of them here. Then if it is an infeasible counterexample, we can dump again this particular path that we found that is infeasible. We can put this also in a witness. Let's call it path witness, because there is no specification to be violated. And then use a precision refiner to go over that path and detect some predicates, for example, that we need to track in the abstraction. And then we can put these predicates in the invariant witnesses as invariants over a path. And they are not loop invariants now, but they are invariants over the path. And the model explorer can pick those invariants from the witness. And so we have moved basically from the information from one component to the next component using established exchange formats, right? So remember the problem that we have is we are missing containers for the information that we can pass from one verification tool to the next. So this worked actually, but there's a but. It was pretty inefficient, because those witnesses here, they were not made for this purpose. So there was an overhead included. And then what we tried is, okay, let us introduce a new format that is better tailored to this process, and then see how the performance is. And then we saw that, okay, if we use formats, we used simple YAML format to pass information around, then this was much better. And then it is almost as good as the native implementation of it. So what comes as an overhead basically is these are each time processes that we start, right? And if these tools are implemented in Java, then we have to start a Java virtual machine each time. So there's a certain slowdown for sure. But this can be healed by implementing these as a service, for example, and query them so they are started and running all the time. But what we have showed is that this component can be used from verification tools, for example, from CPACHECKER or Ultimate Automizer. Feasibility checkers. There are many validators around. Even you could use bounded model checkers here, because the passes are finite, right? And bounded model checkers are perfectly fine with verifying whether the bug is on a certain C program that represents only one path. And here we have also experimented to use various precision refiners. For example, we have used Ultimate Automizer, Precision Refiner, and CPACHECKER's Precision Refiner, and try to exchange them and see which one is better. So, yeah, decomposition is possible, but we need to find more opportunities to decompose and use off-the-shelf components. Then we had looked at, is it possible to, currently there are two schools of thought in verification. There are automatic tools like data flow analysis, software model checking, and then there are the deductive verification tools or interactive verification tools. The interactive verification tools are way more expressive and powerful than the automatic tools, but the automatic tools, they scale better. They can handle hundreds, thousands lines of code where you cannot deal with adding annotations for 100,000 lines of code. But if we compare little programs, then the essential information is in both. So this is a pharmacy style program. So if you use pharmacy to prove this, then interactively you have to add this loop invariant, for example, so that pharmacy is able to prove this program correct, right? And if we look at our witness from the automatic verifiers, we also have, we have an invariant written that x equals y. Right? So can we exchange this? And yes, we can. Why don't we, help these tools to understand each other by constructing transformations, simple syntactic transformations. So given such an annotated program, let us turn this into a witness that contains also the invariants and that we can give to a validation or verification tool to prove correctness, or vice versa. If the automatic verification tool has found out what the invariant is, let's put this as annotation in the program so that an interactive tool has easier task to do. Right? If you, I don't know, if you have already used an interactive verification tool, it's at the beginning it's cumbersome because you have to add like trivial invariants, like x is greater 0, something like this. So there are always these trivial tasks that you have to do and that stop you from progressing. And maybe you can use automatic tools to find out all the easy stuff to get rid of and only think about the real difficult thing that where we need a human. So what can we do there? With our pictures that we introduced for types, I want to express this. So we can turn a witness validator, we have 10 of them, into an interactive verifier by saying, okay, if we have a program with ACSL annotations, we can grab the annotations, put them into a witness. So this transformation gets the program and peels out the invariants and write them into a witness, and then a validator can be used to verify it. Or let us turn an automatic verifier into an interactive verifier. How can we do this? So what is an interactive verifier? And the input is a program with annotation, and the output is the result, right? So we can use the program, turn the ACSL annotations into witnesses, then turn the witnesses into asserts, right? So if the witness contains an invariant, we can put an assert statement into the program that is violated, if the invariant does not hold. So we can reduce the validation problem to a verification problem, and then use an ordinary verifier to analyze. You see, this is a different specification here. The specification now has, in addition, check all these assertions that we have introduced for the invariants that we have checked. So just with, these two are not intelligent tools. They are just transformers on a syntactical level. So we just basically bridging the language between these two kinds of tools. So further, what can we do? We can turn an interactive verifier, and we took pharmacy as an example, into a validator to use those strengths that these tools have. So we do the other way around, right? We take a witness and put the information from the witness into the program as ACSL annotation. There's a prime missing. This is now a changed program, right? And then use the verifier, the interactive verifier, to prove the program. Or we can turn an automatic verifier into a validator. This was actually published already in another concrete way, but here it's now in this framework. So we take the witness, turn them into asserts, and use a verifier to validate that all these invariants that are written as asserts are really holding. Yet another, and this is the last one, loop abstraction. So programs can contain difficult, sophisticated loops. And people in research have found out that one of the approaches is to abstract away from loops, or not abstract away, but make the loop more abstract. So let's look at this example here. We increase, we have I, we increase I, and in the end we assert that I is greater or equal to n. This is the control flow automaton. Basically, it's an internal representation of the same program. So this is the loop here. We increase I as long as I is not equal to n yet. And then we go out and we have an error if I is less than n, right? And now we could abstract. We could abstract from the loop by saying, oh, we havoc the value of I, which is changed in the loop, which is the only variable changed in the loop. We say, okay, let's have this a non-deterministic value, and since it's in the loop, and we know that it leaves the loop only if I is greater or equal to n, we put an assume here, right? And then we can prove this program correct. So this abstraction is called Havoc abstraction. It's the most simple loop abstraction than you can imagine. It's really also not very powerful, but it helps here to prove this program correct, right? So we can erase this while loop and put in this piece of code there in order to prove correctness for this little program, right? So now, how is this useful in combinations? So there are tools that implement loop abstractions, but this does not have other tools, right? So there are smart researchers implementing clever loop abstractions, but it does not have other researchers. So what we have to do is, let me skip this one. What we have to do is we have to make the loop abstraction accessible. So we have written a tool that implements a couple of these loop abstractions and spits them out. So input is a program, and the output is not a verification result, but is a simpler program where the loops are abstracted away. And then we can use arbitrary verifiers. So if a verification engineer wants to try out loop abstraction, they can use this tool, give the program as input, get the transformed output program as output, and use this for verification. And so what we have also implemented to produce patches so that the patches can be maintained and used and passed around to other tools also. So the idea is to identify approaches that are good for verification, but make them accessible in a way so that other people can use it without having to dig into the program and change and manipulate the implementation of the verification tool. Right? Verification tools are very complex software systems. You usually don't want to dig into the code and change it. And this way, basically, what we have now here is it's a new kind of artifact. It's a program with abstracted loops. The nice thing is it's still nothing new because it's C syntax. It's just an ordinary C program where just a few lines of codes were changed. Okay, so this ends my presentation. So the point I wanted to make is there are external combinations possible, and I think we need to go the direction to see verification tools as libraries or as off-the-shelf components that we can use and should use. But we need interfaces, and we need more interfaces. So I have outlined and gave you an idea of how interfaces could look like, but there are many more, but we don't know yet them, right? And there are combinations, and there is cooperation, and there are many ways to do it. We have to investigate more of them, and yeah, we by leveraging the cooperation between tools, we can maybe improve the power of our research community. And I hope I made you excited a little bit about cooperative verification. Thank you for listening.
Thank you. Thank you. I think this really gave us new insights and ideas for new directions. So, any questions? Yes, please.
Thank you for the talk. I have two questions. Have you been in touch with the pharmacy team? I think we would be very interested by your work. Actually.
Sorry,
have you been in touch with the pharmacy team? Because we would be interested with your work.
Can you say that?
Have you been in touch with the pharmacy team? The guy who works in pharmacy.
Yes.
Have you been in touch with them?
No.
To them? Because I think we would be interested in your work.
Are you from the?
Yeah.
Oh, okay, cool. So let's talk.
Yeah, absolutely. After that, before that, the second question on your Havoc loop abstractions, how do you handle more complex C structures like memory accesses and stuff like that? Because it sounds like complicated to just wash it away.
So the first approach in Havoc abstraction is just get rid of it. So the idea is Havoc abstraction hopes for that the changes made in the loop are not influencing the correctness of the result, right? So whatever the complex structure includes is not important for the correctness of the program. Let's get rid of it and see if we can prove. So for example, in this example that I had, the specification was just talking about the loop counter, right? And nothing else, not what was done with the loop counter inside the loop. So this is the hope. If correctness cannot be proved, then the abstraction was not good enough to prove anything, right? So if you find a counterexample in the new abstracted program, then you know nothing, right? You know only that the abstraction wasn't good enough. So what we have done in this work actually is we have implemented several loop abstractions, and this was the slide that I skipped. So we have, let's say we have loop abstraction A, B, C, and we use CEGAR on the control flow graph. So we first try A. If this does not work, we try B. If it does not work, we try C. If this does also not work, then we have to try to verify the original control flow.
But the second example was a case where the abstraction is too simple, where it's no longer divisible by 4 if it's a non-deterministic number.
Yes.
It's not in general.
I have been a few large abstractions in OK to me. Mostly we can say we don't know anything about the program, but if you don't handle memory access, I guess you would forget to expand some variables. It says this one is non-determinant too. How do you handle the fact that maybe you will have a state at the end of the loop that is wrong because you forget to forget information and stuff.
Yes.
How do you manage that?
No, we just don't.
Okay. Thank you very much.
Mm-hmm.
Yeah, thank you for the talk. I have a question about witnesses for verification techniques like symbolic execution or model checking, where you've explored the state space. How do you have a witness for the fact that I've explored the state space?
Mm-hmm. So if an explicit state model checker or a symbolic execution model checker has does not compute invariance, then the witness would be a huge monster of
Right, like here's all the paths,
yes.
and even then to validate them would essentially just be reperforming
The validate, yes, the
the
validator
symbolic
would-
execution, so the validation wouldn't be any faster than the verification.
Exactly, that's true, yes. So for explicit state model checking and symbolic execution that does enumerate all states, it's not very helpful. But there are like modern symbolic execution tools. They are hybrid in a sense, and they compute invariance also. So, for example, there's one tool that participates regularly in the competition. It's called Symbiotic. That it works like it first does lots of program transformations and slicing and so on, and then it has a symbolic execution engine, and the symbolic execution engine is able to come up with invariance. So I think the pure old-fashioned like King 70-something approach to enumerate parses, I think this is only used for test case generation. And even in test case generation, we have concolic approaches and so on. But you're right. That's the problem.
I still think there's some advantage because you have to avoid exploring redundant paths in the state space search. And if you give a set of paths that are explored, so that part at least is taken care of.
But you still have to sort of trust that you eliminated the redundancy.
So for the violation witness, right?
Yeah.
Because then there is this one path on which the violation helps, and then this one path is done.
So thanks so much, very interesting talk. So some question is that probably all your assumptions really use the same language like the C. Just wondering, in the typical model checking, also many model checkers have different model languages like scaling program, US and US. So do you have some insights about how to combine using this cooperation approach to integrate different model checkers, different model languages?
You mean how to integrate different model checkers for different languages?
Yeah, like script and US and US.
No, I have no idea.
Okay.
So maybe the more we work on this, the more abstract get the exchange objects that we have, right? And if you come up with saying, okay, we have reduced information that we share to just the line number where the invariant belongs and the invariant itself, and maybe then the invariant can be expressed in a common format like SMT, and then it can be used by other model checkers to be validated or to be exchanged. But so far, new SMB is not for a programming language, but for a model language for transit systems, right? And yeah, why not? I mean, the invariants look similar. Why not make them exchangeable?
Thank you very much for the talk. It was really interesting. One question that I have is about the configuration of these tools, because some tools, yeah, have a lot of configuration options. They have different trade-offs between position and performance that can be obtained. And so, is that an overhead, or is that an obstacle when you try to combine the tools together?
Yes, this is not only for me as a verification expert, but especially for the users, it's an obstacle. And so in the verification community, for the combinations that I worked on, I took the tools and the readily configured options and so on from the competition contributions. So the yearly evaluation has the advantage that the tool developers that participate in the competition, they tell us what they think are the best options, right? Are the best options. And then I, as a user, would take those options because they used it for the competition. Competition has a diverse benchmark set, and therefore it should work for my programs also.
Okay, I see.
But in essence, the verification tools, they should offer some help to the user to how to get the right options, right? And there is no solution yet for this. Thank you.
Thanks for a very exciting talk, and I really like the idea of pre-processing that reducer. And do you have any, or do you have your favorite processor that can be, whose result can be used by multiple verifier?
I didn't understand.
Like you say that like you may the cooperative way of verifications that the verifiers may share results or communicate, and then you use reducer or other preprocessor to produce some intermediate result.
Yes.
Do you have some your favorite one whose result can be used by other verifiers, or make the verification easier for the other verifiers?
No, it's not yet enough explored to have a general answer to this. So what we are currently working on is a, so we have, okay, step back. So how would you parallelize a SAT solver? SAT solvers use the DPLL, and there's a clause, there's a set of clauses that are learned from the formula. And if you want to parallelize, you can use a common set of clauses, and the different processes use the same clauses. So if I transfer this idea to software verification, what I would imagine is I have like n processes with I don't know, CPACHECKER, ultimate automizer, K induction one-hole checking, whatever. Let's say 100 processes, and once they have a hunch of, okay, I think I have found an invariant, let's put the invariant into invariant storage, right? And then all verifiers basically can dump invariants there and can take them out. So all tools can benefit from invariants for parts of the programs that other tools have found already. And maybe in parallel also validators should be run to verify whether the invariants are actually correct, and maybe label them in the invariant store. Okay, check mark, this invariant is really an invariant, you can rely on it, and this one is just a candidate invariant. This is proposed by a tool, but is not yet validated. So I think invariants are the best, what I like most is an, if you wish, exchange format. But yeah.
Actually, this leads to a question that came up to me. Do you think we will find ways to communicate more specific properties that are not maybe expressible as invariants so well between verifiers? So one could be access to this data is race-free, or there is a thread that is ready to receive a signal at this point anytime in the execution, or that this data structure is, for example, doubly linked list. So sometimes the invariants could be very slow or complex, but sometimes you can't even express them as code. So how are we going to share such information?
Good question, right? So yeah, I mean, what we could also put in this common store is suspicious events, right? So one verifier found, oh, this might be a memory leak, or this might be a invalid dereference or so. Have a look at this, mark this program location as problematic, and maybe attach a label which is not an invariant, but which states that this has a problem with memory, or yeah. But this is really a thing that we all know that we need it, but nobody sits down and specifies how to express it, right? And maybe the reason why nobody does it is because we don't know really what to say, how to write it. And I think it's a process. We need to, stepwise go ahead and improve a bit, and in the end we will know what we need to write down.
Yes, I agree. We need something like an API to share this data. Okay, so I'd like to thank you again. So,